So we saw in the last problem that we can do an upper and a lower sum, but that's a lot of work to do two different ones. And in the last video, I only did half of the problem for you. So what we would really like to do is just do one sum for all of them. And basically what happens is instead of doing n rectangles, we want to do an infinite number of rectangles. Okay, when we do an infinite number of rectangles, it doesn't matter if we're doing the upper or the lower sum because they're going to be the same. So that's what this says. If we have a function that's continuous and non-negative on an interval, as we get an infinite number of rectangles, the upper and lower sums exist and they're equal to each other. So that's what we want to do is we want infinite number of rectangles. So the area under a curve, okay, it's bounded by this curve and these vertical lines A and B. Okay, here's A and here's B. It is this. The area is we have an infinite number of rectangles. We're taking the sum of all of those areas. F of ci is the height of each rectangle, and delta x is the width. Okay, so it's just base times height of a rectangle. We're going to add up all the rectangles together, and we're going to do infinitely many of them. Okay. Now, to find the width of the rectangle, delta x is the width. That's b minus a over n. And then to find the height, you need to plug in ci, and that's going to be a plus I delta x. These are the three pieces that you're going to need to do all of these problems. So make sure you have them down in your notes. We'll tackle one of these. So we want to find the area of the region bounded by the graph of f of x equals x cubed, the x-axis, and the lines 0 and 1. So let me just sketch this for you. You know what a cubic function looks like, sort of like that. So from 0 to 1. So we're looking for this area under the curve right there from 0 to 1. So what we're going to do is to find that area, we are going to do an infinite number of rectangles. So it's the limit as the number of rectangles approaches infinity. We're adding up the area of all of those rectangles. And we need to multiply the height of the rectangle times the width of the rectangle. Okay, so now we need to know what delta x and ci are. So remember, delta x is b minus a over n. B and a are 0 and 1. So delta x is going to be 1 over n. So all of our rectangles are 1 over n. And then ci, remember that's a plus I delta x. In this case, a is 0. That's our first part. And then we just found delta x was 1 over n. So ci is I over n. So I'm going to come up here and plug those pieces in with a pencil. That is my goal. So it's the limit as n approaches infinity from 1 to n of f. Remember, ci is down here, I over n, and delta x is 1 over n. All right, the next thing we want to do is f of I over n. We're going to plug that into this function. So it's the limit as n approaches infinity from 1 to n. We're plugging in I over n into the function. So that's I over n cubed times 1 over n. So we have the limit. So our numerator is going to be I cubed, and our denominator is going to be n to the 4th. Okay, let's keep going. We'll come up here. So still, we haven't done any with the limit yet. We'll get to that in a little bit. What we want to do now is simplify this summation. Now, n is technically a number, okay? It's a really big number, infinitely huge, but that's a constant, so we can pull out the 1 over n to the 4th. And then we have this summation, I cubed. Now, let's keep going here. Still haven't done anything with the limit. We'll get to that. this part right here, this thing, we can use one of our formulas from yesterday. It's on page 291, I think. But the formula for I cubed is n squared n plus 1 squared over 4. And again, you don't have to have that memorized, but you do need to be able to go get it and find it when you need it. Okay, now we're going to simplify this. I'm going to start by canceling some n's because I can. So remember, we still haven't done anything with this limit. We will get to that. The numerator, I'm going to FOIL that out. So it's n squared plus 2n plus 1. And the denominator is 4n squared. And now I'm going to divide each of those pieces by 4n squared. So n squared divided by 4n squared is going to be 1/4. 2n divided by 4n squared is going to be 1 over 2n. And then 1 divided by 4n squared is 1 over 4n squared. Okay, now I am going to take the limit. Okay, so the limit as n approaches infinity. Now, this first thing is just 1/4, so we just leave it as 1/4. The next part, when you plug in infinity, 1 divided by 2 times infinity, that is going to approach 0. And 1 divided by 4 times infinity squared, well, that's 1 divided by infinity. That is going to approach 0. Okay, so our answer is 1/4. This area right here, under the curve between 0 and 1, is 1/4. Exactly. Okay, so that's how we use these triangles to find area under the curve. Okay, I will show you, I am not going to show you example number 6 in a video. You can look over that on the PDF. Okay, it's a similar problem, but you can kind of see how I broke that down. So check on Google Classroom for that. And then I'll show you some videos for the next few problems.